One's the
power. So does it make sense what you'd plug in for each of these? This is just the normal G. This big M is the mass of what? Earth. The mass of the object itself cancels out. That doesn't matter. It doesn't matter what the mass of the satellite is. T, we just figured out what it is. And if you plug all that in, you get 4.2 times 10 to the 7 meters. This, if you look up the radius of the Earth, to compare, because this is just some big number, right? 4.2 times 10 to the 7 meters. If you look up the radius of the Earth, do you have a feeling for how many times the radius of the Earth is? This is?
Not sure.
This is 6.6 times Earth's radius. So, did we draw this to correct scale? I would not say so. Right, so here's 1 R. We need 5.6 more R's to get out to the actual distance if we were to draw this to scale. So if you were saying height above the surface of the Earth, then it wouldn't be 6.6, it'd be 5.6, right? Because you'd be saying from this point here, how high up would it be? So that and then 5.6 more, like maybe about right up there. It's pretty far out. It's a lot farther out than a lot of the other satellites. Most satellites that we put into orbit, we put just high enough so that it's above the atmosphere and they don't burn up in their fast orbits. Because then they're just more convenient. It requires less energy to get there, blah, 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 blah. So most things we have are in an orbit that's like very close to the surface. It's called low Earth orbit. But another main category of where to put things is this geostationary orbit. It's a very useful thing. Okay, let us just briefly consider a case where we do have a changing speed, just to make sure it's clear how to take that into account. And there is a homework problem that's very similar to this. Example 2. What is the magnitude of A if going around an R equals, let's make it 10-meter circle. And, oh wait, we have to say how fast. At, let's make it 20 meters per second. And here's the big and speeding up. And the rate of speed up is 1 meter per second squared. So let's make sure that we're comfortable with what that kind of looks like. Let's draw our little picture again. Something's going around a circle. Here's R. Here's B. The only difference here now is there's going to be a component of speeding up, acceleration due to speeding up that's in that direction, as well as the component that's keeping it into the circle, which would be that direction. So remember the equation overall is this. dv dt in the v hat direction minus v squared over r in the r hat direction. V hat and r hat directions are perpendicular to each other. So if you want to know what the overall magnitude of this is, and you have something here, and you have something here, right? Because in this case, what's going for this? 1 meter per second squared. This is changing.
Yep.
Here, it's going in a circle. So you know what V is and you know what R is. So you have non-zero things here and here. But what we want is a magnitude of A. If you want to know what the magnitude of A is, how do you get it from knowing what two perpendicular components are? Components in two perpendicular directions.
Pythagorean theorem.
Pythagorean theorem. So that means a is the square root of, what's the way of writing it here?
What?
So I'm using Pythagorean theorem to say what is the magnitude of acceleration if I have these components. So what is the way of writing that then? So here are two perpendicular directions. Here's the component in one direction. Here's the component in the other direction. And now we're just using Pythagorean theorem to write what the magnitude is.
Yeah, term 1 squared minus or plus term 2 squared.
So one term squared plus the other term is minus v squared over r squared. And if you plug in those numbers, what you'll see is that this term ends up totally dominating over this term. I mean, you're just plugging in the numbers that are here. It turns out with those numbers, with this just being 1 squared, this ends up being by far the dominant. One thing to watch out for when you do this, this v is squared twice. So don't forget that there's a v squared in here and that it's squared right there. But if you plug that in and just keep 2 decimal places, you just get 40 meters per second squared, which is what you would get if you didn't even have that term actually. So to 2 digits, this is kind of negligible. But that's in principle how you do it. You have to include both. Does that all sound good? So that's using like the full-on version of this to figure it out. And let's talk just briefly about this really cool other thing that many of you mentioned thinking was cool, and it is, which is banking. Not like banks and money, but using banking like with an airplane or a car or something like that to help you turn. So that will be example 3. Ready for me to erase it? Ahmed, you're staring at it. Ready for me to erase it?
Yeah, I'm good. Thank you.
Come on, I'm going slow.
Set your line up for today?
It's good.
You set your line up for today?
We'll read that ad down.
Example 3, banking. Let's just talk about setting up the equations and how they work. You can plug in numbers and use one of your problems in the homework ends up plugging numbers. Okay, so here's the thing with how banking works, right? If you have something that would normally be moving along like this and be feeling either lift from the, like it's an airplane, the lift comes from basically the airplane pushing down on the air and the air pushing back up. Or if it's a car, then it's the normal force, right? The car's weight is pressing down on the surface of the road or whatever, and the normal force of the road is back up. But if you do it at an angle, then interesting things happen. So here's the object that's at an angle. It could be an airplane or a car on a slanted road. You've got gravity down, and here's the interesting thing. You've got F lift, you could call it, or normal force if it's a car going around a bend or something like that. And it's not lined up. That's the idea of it. And here's some angle, the kind of the banking angle. So let's use F equals MA. We'll take a common, approximately true common situation, which is that overall it's staying at the same level. Like the airplane, we're not talking about taking into account either the car like crashing through the surface or the airplane changing height. We're just going to take a case where we know that it stays at the same level. So vertical components cancel if height doesn't change. And let's just write out F equals MA for that. What are the components in the vertical direction? John, components in the vertical direction?
Gravity.
Thank you. Minus FG. And then what? What else has to cancel with it?
Then negative. Oh no.
Well, we make, I'm just making this correct. It doesn't matter which way to do it. But let's say we choose down as negative. Then it's
That up, yeah, that's right. Well, that's positive first.
which so how do we get the right component out of that?
Cosine, yeah.
F1 cosine theta.
Yep, or I'm calling it FL for lift, but either way, it could be normal force, cosine theta equals, and on the other side is NA, but for this situation, we're saying that that is equal to 0, because we're saying that its height is not changing. So there's one equation you get out. Then the horizontal components, provide acceleration to move in a circle. So let's write out F equals ma for that. What do we have component-wise in the horizontal direction? FL sine theta. And we can choose either direction as positive or negative. It doesn't really matter. Do you want to make it negative or positive?
Positive.
Positive, sure. FL sine theta. Any other components in the horizontal direction? So that's the F side. Now the MA side. So M, the mass of the airplane or the car or whatever it is we're talking about here. And A, now we can say something about A if we know that it's moving in a circle.